Good morning and once again welcome to our Lesson 1 continuation in sections 1.6 and 7. A charged object has potential energy by virtue of its location in an electric field. For example, in this figure, consider the particle with a small positive charge located at some distance from a positively charged sphere in figure letter B. If you push the particle closer to the sphere, you will expend energy to overcome electrical repulsion. That is, you do work in pushing the charged particle against the electric field of the sphere. This work is done in moving the particle to its new location, that is, it increases its energy, and we call the energy of the particle possesses by virtue of its location electric potential energy. If the particle is released, it accelerates in a direction away from the spheres, like next in the figure B, and its electric potential energy changes to kinetic energy. Say for this figure in here, there's a spring. If you expand and compress the spring from its equilibrium line in here, the corresponding potential energy from this figure also increases. For example, if you compress that, the dot from this line here goes upward. So the potential energy of the compressed spring also increases. Same is true when you are expanding the spring. The figure in here goes upward again, and the potential energy is also increasing. This is the visualization of what is happening in an electric potential energy. To consider the electric potential energy per unit of charge, we simply divide the amount of potential energy in any case by the amount of charge, and the concept of potential energy per unit charge is called electric potential. In this equation 1.7a from your handouts. And the unit of measurement for electric potential is the volt. Electric potential is often called voltage. A potential of 1 volt equals 1 joule of energy per 1 coulomb of charge. That is in equation 1.7c from your handouts. Thus, a 1.5 volt battery gives 1.5 joules of energy to every coulomb of charge passing through the battery. Both the names electrical potential and voltage are common, so either may be used. Suppose the electric field in which charge QO in here from this figure, QO moves, it moves, that is caused by several point charges Q1, Q2, and Q3 at distances R1, R2, and R3. We conclude that the potential energy associated with the test charge at point A in this figure is the algebraic sum, and it is not in a vector form. So algebraic sum of this figure is equals to this equation 1.8 from your handouts. And we can represent any charge distribution as a collection of point charges. For every electric field due to static charge distribution, the force exerted by that field is conservative. Learning activity 1.4 entitled A System of Point Charges. 2 point charges are located on the x-axis. Q1 equals negative E at x equals 0. So if we have an x-axis, there's a 0, and there's a 1, and there's a 2. And this is a positive scale, and going to the left is the negative scale, but we don't have any negative distance, so let's just consider the positive distance. So from the problem, the Q1 is located at x equals 0 with its charge negative E, and Q2 located at x equals to A or 1A is positive E, and the third point charge Q3 located at x equals 2A, that's 2A, is positive E. Find the total potential energy of the system of three charges. The figure below shows the final arrangement of the three charges, and we use equation 1.8 to express for the potential energy of a collection of these charges. The total potential energy of the three charges are in this equation. By using this equation, we can get the relationship of those three charges. So the charge Q1 in relation to charge Q2, charge Q3 in relation to charge Q1, and charge Q3 in relation to charge Q2. You can interchange that because, by the way, you are just referring to their distances, R1 and 2, R1 and 3, and R2 and 3. And now we can get for this Q12 over R12, it means that the Q1 in relation to Q2, and that is Q1 is negative E and Q2 is positive E. So put that in here, and their distance is R12 is equals to A, and this is or 1A. That is why it is A. Next, Q13, it means charge 1 in relation to charge 3, and their distance is equals to 1A plus another 1A is equals to 2A, or that's just 2A. So put it in here. And Q1 is negative E, and the Q3 is positive E. Next, Q2 in relation to 3, and the charge 2 is in here located. That's located at x equals A, and their distance is 2A and 1A. So 2A minus 1A is equals to, again, 1A, or simply A. And their charges are positive E and positive E. If you do multiplication or mathematical skills, if you applied it in here, you can get this equivalent. So retain the K, and the common division of the common denominator in this equation is 2A. So if you are doing a mathematical calculation in here, can get negative E to the positive 2. Next. We are now in capacitor. So what is a capacitor? Electric energy can be stored in a common device called capacitor, which is found nearly in all electronic circuits. And a capacitor is used as a storehouse for energy. From this figure, you can see that this capacitor has 470 microfarad, 1000 microfarad, and 202,000 microfarad. The simplest capacitor is a pair of conducting plates separated by a small distance. So from this figure, when the plates are connected to a charging device such as the battery in this figure, this occurs that the positive battery terminal pulls electrons from the plate connected to it. These electrons Okay? These electrons are transferred from one plate to another. And in effect, they are pumped through the battery and through the negative terminal to the opposite plate. The capacitor plates then have equal and opposite charges, and the positive plate connected to the positive battery terminal and the negative plate connected to the negative terminal. The charging process is complete when the potential difference between the plates are equal and the potential difference between the battery and terminals are equal. So the greater the battery voltage and the larger and closer the plates, the greater the charge that can be stored in this circuit or in this capacitor. In a circuit diagram, a capacitor is represented by either of this symbol. So one common way to charge a capacitor is to connect these two wires to opposite terminals of a battery. And once the charge Q and negative Q are established on the conductors, the battery is connected. So Q is the charge and C is the capacitance. Say in this equation, capacitance C is equals to Q over potential difference VAB. And this capacitance has a unit of farad in honor of the 19th century English physicist Michael Faraday. And 1 farad is equivalent to 1 coulomb per volt. So, tandaan niyo yan na. Now, capacitance is a measure of the ability of a capacitor to store energy. Okay? Capacitor is the device. Capacitance is kakayahan ng capacitor kung gaano kalaki yung kaya niyang ma-store na energy. So, in this equation 1.10, capacitance is also equal to EO times area of the capacitor over the distance between the two plates within the capacitor. Equation 1.10 is used for calculating the capacitance of a parallel plate capacitor in vacuum. The capacitance depends only on the geometry of the capacitor. Geometry is the area and its distance, okay? It is directly proportional to the area of each plate and inversely proportional to their separation D. The quantities A and D are constants for a given capacitor and is a universal constant. Equation 1.11 in relation to equation 1.10 is another presentation of electric field. Electric field is equals to the charge over EO times A. And it has a unit of 1 farad equals to 1 coulomb squared per Newton meter or 1 coulomb squared per joule. Then EO is a constant with a value of 8.85 times 10 to the minus 12 farad per meter. 1 farad is a very large capacitance. As the following example shows, in many applications, the most convenient units of capacitance are the microfarad and the picofarad. And for this figure, you can see that there's a microfarad and 1000 microfarad and 470 microfarad. When we say micro, that's power of 10 to the minus 6. When we say pico, that's power of 10 to the minus 12. Learning activity 1.5 entitled Size of a 1 farad capacitor. The parallel plates of a 1 farad capacitor are 1 mm apart. What is their area? Now, we have given a capacitor 1 farad and its distance 1 millimeter apart. So, the target variable in here is the plate area. And we can solve this by using equation 1.10. Now, area is equals to C times D over EO. From equation 1.10, capacitance is equals to EO times A to the D divided by D. But if you do multiplication relationship conversion, you can get A equals CD over EO. And you can just input the value of capacitance, which is the 1 farad, and the distance of 1 millimeter. Milli, it means 10 to the minus 3. And that is 1 times 10 to the minus 3 meter. And the EO is given constant value of 8.85 times 10 to the 12 farad per meter. We cancel the farad, and we will only get meter and meter. Since this is a division, farad per meter, it goes up to have m squared. And that's the dimension of area. Now, area is equals to 1.1 times 10 to the power of 8 meter squared. Next is the learning activity 1.6 entitled Properties of a Parallel Plate Capacitor. The plates of a parallel plate capacitor in a vacuum are 5 mm apart and the area of each plates are 2 mm squared. A 10 kV potential difference is applied across the capacitor. Compute the capacitance, the charge on each plate, and the magnitude of the electric field between the plates. And for this problem, we have given the value of area 2 mm squared, the distance D 5 mm apart, and the potential difference VAB equals 1 times 10 to the 4 volt or 10 kilovolt. That is just equal. The target variables are capacitance, the charge, and the electric field magnitude E. And we can use equation 1.10 to calculate for the capacitance and equation 1.9 to calculate for the potential difference VAB to its charge Q, and also equation 1.11 to find the electric field magnitude. For the capacitance, equation 1.10, the EO is given 8.85 times 10 to the minus 12 farad per meter. Area is also given 2 meters squared, and the distance is also given 5 millimeter or 5 times 10 to the minus 3 meter. That is equivalent to 3.54 times 10 to the minus 9 farad or 0.00354 microfarad. For the B, the charge on the capacitor is Q equals CVB. Okay? Or from the original equation, capacitance equals Q over VAB. Now, you need only the Q. So, we have the capacitance 0.00354 microfarad or the original value 3.54 times 10 to the minus 9 coulomb per volt. Again, farad is just equal to coulomb per volt. And the potential difference is also given 1 times 10 to the 4 volt. And you can get charges 3.54 times 10 to the minus 5 coulomb or 35.4 microcoulomb. The plate at higher potential has a positive 35.4 microcoulomb and the other plate has a charge negative 35.4 microcoulomb. Don't be confused ha, kasi ang ating capacitor has two plates and also two different positive and negative terminals. And their charge are overall 35.4 microcoulomb. The electric field magnitude is also can be calculated with this equation, and since there's no sigma given, that is also electric field magnitude is also equivalent to Q over EO times A, and that is the charge is computed from this B, 3.54 times 10 to the minus 5 coulomb, and EO is also given, and the area is also given. Now the electric field magnitude is equals to 2 times 10 to the positive 6 Newton per coulomb. Okay, that's the representation of the two plates of the capacitor. We are now here in the last section of our lesson 1, capacitors in series and parallel. This figure is capacitors in series. It is a schematic diagram of a series connection. Two capacitors are connected in series by conducting wires between points A and points B. Both capacitors are initially uncharged, this C1 and C2. When a constant positive potential difference VAB is applied in here, the capacitors become charged. So the figure shows that the charge on all conducting plates has the same magnitude. So there's the capacitors though in all of these conducting plates have the same magnitude. And to see why, note first that the top plate of C1 acquires a positive charge Q. This is here. The electric field and this positive charge pulls the negative charge up to the bottom plate of C1 until all of the field lines that begin on the top plate end of the bottom plate. And this requires that the bottom plate of charge, the negative Q, is it has to be charged to come to the top plate of C2. Now we're moving downward to the C2. The total charge on the lower plate of C1 and the upper plate of C2 together must be 0. So the total charges in here from this negative terminal of capacitor 1 to the positive terminal of the capacitor 2 is 0, 0. Thus, in a series connection, the magnitude of charge on all plates is the same. To make it simple, capacitance 1 and capacitance 2, capacitor 1, and capacitor 2 have different capacitance, but their charges are all equal. And also, from this figure, VAB is connected from A to C and to C to B. And that is, the potential difference in this line, in this series line, is divided. So there's a different voltage or potential difference flowing from this line C and B, and also different potential difference VAC for this line A and C. And that is why the voltage, the overall voltage, is just a summation of the individual voltages. From your handouts, equation 1.12, following a common convention, we use the symbols V1, V2, and V to denote the potential differences VAC, VCB, and VAB. Now, the equivalent capacitance, CEQ, of the series combination is defined as the capacitance of a single capacitor for which the charge Q is the same as for the combination, when the potential difference is the same. And in other words, the combination can be replaced by an equivalent capacitor of capacitance, the CEQ. From equation 1.12 of your handouts, the reciprocal of the equivalent capacitance of a series combination equals the sum of the reciprocals of the individual capacitance. Okay? So, kita nyo naman, the equivalent capacitance is just equals to the combination of each of the capacitance. The potential difference of the individual capacitors add to give the total difference across the series combination. That is, V total is equals to V1, V2, and V3. And so on. So, V total, in this figure, V total is just equals to V1 plus V2. This figure is a connection of capacitors in parallel. Two capacitors are connected in parallel between points A and point B. In this case, the upper plates of the two capacitors are connected by conducting wires to form an equipotential surface. So they are separate now. Hence, in a parallel connection, the potential difference for all individual capacitors is the same. Ibig sabihin, the voltage difference in here is just the same for the voltage difference in here and also the same for this voltage. Or V total is just equals to V1, V2, V3, and so on. Now, the charges, the individual charges is Q1 and Q2. And the total charge of the combination is just equal to Q equals Q1 and Q2. And their equivalent capacitance is equal to C1 and C2. From your handouts, equation 1.13 is useful for computation of overall charge over volt is equals to individual capacitor 1, capacitor 2, or capacitance 1 and capacitance 2. Equation 1.14 is an equation that is equivalent, or the capacitance equivalent of each capacitance. Okay? C is representation of capacitance of a capacitor. Okay? So, equivalent capacitance is just equal to the combination of C1, C2, and C3. Now, what's the difference between the capacitors in series and capacitors in parallel? Okay, now, in the capacitors in parallel, V over Q is equals to 1 over C1 plus 1 over C2. Wherein in the parallel, Q is equals to V. That is equals to the combination of C1 and C2 and so on. Next, for the equivalent capacitance. In a series, the equivalent capacitance is equals to 1, or 1 over equivalent capacitance is equals to 1 over C1 plus 1 over C2 plus 1 over C3, wherein the capacitors in parallel, the combination capacitance is just the summation of all capacitance. Next, for the potential difference or the volt in a capacitor series, the volt is a combination of all voltages, wherein sa capacitors in parallel, voltages are equal on all of the parallel connections. So, you have to memorize this one for you to compute a problem regarding capacitors connected in series and in parallel. Learning Activity 1.7 entitled Capacitors in Series and in Parallel. In figures 1.14 and 1.15 from your handouts, let C1 and C2 equivalent to 6 microfarad and 3 microfarad respectively, and VAB is equals to 18 volts. Find the equivalent capacitance and the charge and the potential difference for each capacitor when the capacitors are connected in series and in parallel. Solution and identify the setup. In both parts of this example, a target variable is the equivalent capacitance CEQ, which is given by equations 1.12 for the series combination in part A, and by equation 1.14 for the parallel combination in part B. In each part, we find the charge and the potential difference using the definition of capacitance, equation 1.10. So, we are given the value of C1 and C2 and also the potential difference VAB 18 volts. From equation 1.12 for series combination, equivalent capacitance is equals to 1 over C1 and 1 over C2. And when doing calculations, you can get C equivalent equals 2 microfarad. The charge on each capacitor in series is the same as that on the equivalent capacitor. Now, charge is equals to C equivalent times the volt. We are given volt 18 volts, potential different na 18 volts, and C equivalent computed from letter A na 2 microfarad, and it is equivalent to 36 microcoulomb. The potential difference across each capacitor is inversely proportional to its capacitance. So VAC and VCB can be computed using this equation. V1 or V is equals to Q over C. So the corresponding potential difference for V1 in here is just the VAC, and also the corresponding capacitance is the C1, which is 6 microfarad. So that is 36 microcoulomb over 6 microfarad is equals to 6 volts. And VCV or V2 in here corresponding to the charge Q over C2, and the charge is 36 microcoulomb over 3 microfarad equivalent to 12 volts. As a checking, 18 volts is a combination of each of V1 and V2, and 12 plus 6 volt is equals to 18 volts. Okay, again, charge in the charge Q on each capacitors in a series are all equal to 36 microcoulomb. Next, in a parallel connection, the C1 is the same 6 microfarad and the C2 is the same 3 microfarad, and also the volt potential difference VAB is the same 18 volts, but the connections are now in a parallel. From equation 1.14 for a parallel combination, C equivalent is just a combination of C1 and C2, and 6 plus 3 is equals to 9 microfarad. The potential difference across each of the capacitor is the same as that across the equivalent capacitor. So, VAV 18, also the voltage here is 18 and also the voltage here is 18. And the charge on each capacitor is directly proportional to its capacitance. Meaning, Q1 is equals to C1 times V, or the corresponding charge is equals to C1 times the volt. So, C1 is equals to 6 microfarad times 18 volt, that is equals to 108 microcoulomb. For Q2 is equals to C2 times 18 volts, and that's 54 microcoulomb. Now, learning activity 1.8 entitled A Capacitor Network. Now, we are given a capacitor with their equivalent capacitance of in each of its capacitor. Find the equivalent capacitance of the 5 capacitors network shown below. So from this network, you can see that it is connected parallel and in series. Where's the series in here? This is the first series, and you can get a parallel line. The next is a series. So first, series, parallel, and a series to get the equivalent capacitance from point A and B. The caption of the figure outlines our procedure. We first use the equation 1.12 to replace the 12 microfarad and 6 microfarad series combination by its equivalent capacitance C prime. How to compute the first equivalent? So this is the original network. We can get the equivalent capacitance from this side, and since this is connected in a series network, we can use equation 1.12 to replace it by 4 microfarad equivalent. And how did you compute that? You just simply compute it by 1 over C prime equals 1 over 12 microfarad plus 1 over 6 microfarad, an equivalent of 4 microfarad. So from this original network, we can get another form of the network. And we will be left with 3 microfarad, 11 microfarad, and the 4 new microfarad. Okay, don't be confused in this because 4 microfarad is just a combination of these two capacitors connected in a series. Now, we have a parallel connection na. Ito sa ating letter B. And when we are solving for a parallel connection, the equivalent capacitance is a combination of the 3 capacitance. So, 3 microfarad plus 11 microfarad plus 4 microfarad is equals to 18 microfarad. Okay? When you're computing a equivalent capacitance in a parallel, it's just a combination of the connections. So, 3 plus 11 plus 4 is equals to 18 microfarad. So, the combination of the 3 capacitors, 3 capacitance is equals to 18 microfarad capacitance. Now, we are left with the last connection, the series one. So, another computation with the use of 1 over C is equals to 1 over C1 plus 1 over C2. That is 1 over 18 microfarad plus 1 over 9 microfarad. You can get the C equivalent of 6 microfarad. So, the total equivalent capacitance of the network is 6 microfarad. This is the answer now. That ends our lesson 1, electrostatics. Up next, you will be answering learning evaluation that I will be posting in our Moodle, and see you again for the next lesson.